So this is going to be a hopefully short video where I'm going to showcase both my game engine that I built and the voxel terrain generation engine that I built on top of it. So we're going to start it up. Just our generic load screen. So what I want here is a seed. And for those of you who aren't familiar with how procedural terrain generation works, basically seeds are a way to specify which world we want to generate. So for every single seed, there's a unique world that can be generated. So if you want to go back to a world that you already previously created or used, you have to give it the same seed. So if, for example, I give it seed 1, which I'm not going to, it would always generate the same world. No matter how many times I closed and exited, it would always be the same world, which is nice if you want to return to the same place. But if you want to have something new and try something new out, all you have to do is hit randomize. It's going to give us a random seed. You can type one in if you want to. And we'll start generating. So our load screen is just going through the process of the terrain generation. I actually have it mapped out. This is a flowchart I used when I originally created the system. It's a very straightforward queuing system at the face value, but it gets more complicated once threading comes in. So basically we just need to understand that to generate procedural terrain, you need to divide things into distinct steps. So we have our first step, which is our actual generation of the data, and then we have the next step, which is the octree creation, and then we have our model creation and our geometry creation. And again, it's not really all that complicated when you just look at it like that, but because I use a very lock-free approach to multi-threading and everything is done together, and nothing's explicitly synchronized. It's all just done as is and when it's done processing itself. So you get a lot of conflicts that can only be solved by explicit management and actually going through and looking at where problems are going to be and grouping things together that are part of the same task. So this is the actual process. I'm not going to go into that much detail because if you're interested, you can ask me. It's quite complicated and long. Alright, so this is the actual terrain that was generated. As you can see, it looks semi-realistic. It's kind of up to you to specify how realistic or not realistic you want it. Right now, the terrain is being generated using a couple different noise functions. So initially we generate the noise using a 2D height map that basically just specifies the maximum height of any XY or XZ position on the world grid. Then we take another noise function, which is actually a 3-dimensional noise function, and it represents our density, and we use that to weight the height value at every single position. And that allows us to have unique things like overhangs and caves and stuff like that, tunnels. Then finally, we take another 2D height map, which represents erosion and softening and stuff like that, effects over time, and we apply that as a gradient onto our previously combined and fused height map and density map. And that allows us to have, a lot better, I would say, transitions between two different levels of complexity for erosion and stuff like that. It makes the terrain look more natural and smooth and realistic. So right now, for the rendering, what we're using to shade and texture the terrain is a shader that is based on the slope of the terrain. So we can change this in real time, though, as we'll do right here, to this shader. So what this shader is doing is it's actually shading completely based on the height of the terrain. So if you take a XZ position and you look at its Y, if it's past a certain Y threshold, it's the green grass, and if it's below a certain Y threshold, it's just brown or dirt. It's just nice to use to see how the elevation changes over time. And lastly, we'll switch to another shader that represents the normals of the vertices in our grid. So why this is useful is because a lot of the time when you're looking at people who've created terrain generation systems, and they use a lot of algorithms such as dual contouring, which is what I'm using, or marching cubes, or dual marching cubes, or extended marching cubes, there's a bunch of them, surface nets, they have problems with normal vectors. And most of the time the normal vector problems are either code-based, as in it's a programmatic error, or it's an error based on the solving of the quadratic error function, which we use to... The quadratic error function is the mean squared error, which basically we can just use to approximate a point on a surface edge crossing position. because of the complexity of that step, even just saying it out loud is pretty complex. There's a lot of issues where people don't do it quite correctly, and then you get very incorrect normals that are approximated just so wrong, which is usually, it boils down to some sort of matrix solving error, because you have to use a system of linear equations. But as you can see, there's no problems with my normals. Normally you would be able to tell if there's problems. There would be artifacts, like you'd get a splotch of red here because the normal would just change out of the blue. But clearly, no problems. Alright, so we're going to go back. Slope. Alright, so the next thing we'll talk about is the level of detail system that I used. And the level of detail system probably is the system in my engine that has gone through the most iterations. I was really struggling for a while to find something that I thought was a good balance of performance and I don't want to say visualization, but it needed to look the nicest. And eventually I actually found an algorithm that not only had the most amazing performance, I also honestly think it looks the best visually. Even the more expensive algorithms produce results that I would say are more questionable in their nature. So as you can see, the level of detail system is actually pretty straightforward. It's just a clip map, which is a way to specify distance from the view representing a different level of detail. So like in the middle right here where we have our highest level of detail, because if you're close to something, you want to see it in the most, accurate way. And then as it extends and expands out from the view, we get lower level of detail. The key thing is I'm actually going to turn off the dynamic loading so we can go down and see these transitions. So originally I didn't use a system that used seams, and seams are basically these stitched patterns that are the edge of every single page, which are the chunks of data, 32 by 32 by 32. The problem with not using seams is that things are connected just explicitly by being like a puzzle piece, and they fit together. When you change one of the puzzle pieces, all the puzzle pieces that are connected to or neighboring it in your von Neumann neighborhood have to be completely regenerated, even if they experience no change. Just because there's a chance there could have been change, they have to be recreated, and this causes a lot of unnecessary overhead. Like it's not a pre-optimization, which is a thing that happens a lot when you're creating a system like this. It's actually a relevant issue, because if you use the system I originally used, you would get horrible lag and horrible freezes when you would try to change things, because there were so many updates going out, and even with grouping and explicit removal of unnecessary operations, like I would go through and check to make sure that everything was being done in a way that wasn't overdoing stuff, it would still just cause so much unnecessary overhead. So I changed to the system. It basically also uses a quadratic error function, because the quadratic error function is awesome, and it uses it to just find the minimum error for removing an edge in a level of detail. And because of this, we can remove any amount of edges in any area while maintaining border vertices clearly, because we don't want to remove anything that's going to change the actual feature points, which is the term that you actually use, of the mesh or the geometry. The level of detail system actually is really nice. I think it's probably one of the best parts of this. It was one of the hardest things to implement for sure. I'll actually go ahead and show you that you can change it in real time too. So we'll go ahead and first let me get the coordinates of this page you're looking at. Alright, and so this first variable or argument is basically just specifying what level of detail we want the pages in the radius that we're specifying to be turned to. And at the moment I'm just going to do all the pages, but the level of detail is an integer coordinate that represents a pre-specified list of level of details that you can actually put right here. So at the beginning you specify what level of details you want. I have 4, so you have 0 through 3. Alright, and then this is just the radius, so how many pages in each direction do we want to have this level of detail. Alright, so as you can see, we changed the level of detail to 0, which is highest resolution, and everything is basically at an unreduced level. Like, there's no level of detail actually going on right now. So, because we're not actually generating that much terrain, as in there's not that much on the screen, the frame rate isn't going to drop that much. But normally, this would actually cause a significant amount of lag because there's no reduction going on, so everything is just maximum amount of triangles. So we'll go ahead and we'll do the same thing, except we'll actually change it so the level of detail is at the lowest level of detail. So 3, 10. Alright, so as you can see here, now everything is completely reduced. It honestly doesn't look all that much different. Clearly there's some things that are pretty drastically changed, but for the most part I would say that if you were looking at it once very quickly, you probably couldn't tell that much of a difference. The other thing I want to point out is that the border stitching or the seams is still here, because no matter what level of detail you're at, those stay constant. And the reason why you do that is because it allows you to change anything you want inside those border regions, and it has no effect on the outside because they're always the same. It's a constant. It stitches it together. Alright, so we're going to go ahead and move. It's going to fix the level of detail. Oh, I have to turn oops. Turn dynamic loading back on. Alright, so as you can see, went back. The next thing I want to show you is the settings that you can actually use for the engine. So this has nothing to do with the train generation at the moment, but I figured I'd just show anyway. The first thing we're going to do is you can just set the camera speed. This just allows you to move faster. All the view controls are completely accessible in real time. They're all done using composition. I'm actually using an entity component framework to basically remove all object hierarchies and all inheritance and anything like that. So everything is done by composition, and it's all in contiguous arrays. The next thing we're going to do is we're going to go ahead and change actual parameters for the train generation, which you can also do real time. Some of it requires a reload because we actually have to regenerate the train based on the new features. So we'll do that right now. The first thing we'll do is we can actually change the scale of the train, and basically what this does is it just allows you to have either more extreme or less extreme train. So we're going to change the scale to be much lower, meaning that things are going to become much more extreme. So we have to go through our loading process again. The reason you have to go through the loading process is because we're actually changing the noise values at these positions. We're not just changing small interpretations of the noise, we're actually changing the noise. So as you see, as I said, it gets way more extreme. There's much higher peaks and there's much lower valleys, and they're happening more often. They're more close together. And this is just because the values that are being output by our noise generation are being scaled down less, so this results in higher value noise. So we'll go ahead and we'll change the scale back. We can also specify the octaves, and octaves are basically sort of a quality control to an extent. It's not unlimited. It basically specifies how many layers of the noise function that you're using you want on top of each other, and this is different than the layering noise that we talked about earlier to get different effects like erosion and stuff like that. This is actually just explicitly saying how many times do we want noise to be put on top of each other to become more detailed. And usually you don't want this below like 10, because if you get below 10 you start getting noise that's very predictable and smooth, and there's not really any uniqueness to it. But anything above 10, you're probably not going to notice that much of a difference. If you have the ability to run it at 12 or 13, I would say go ahead and do it, but I think 10 is pretty much the safe area you want to be at. So as you notice here, we can specify the erosion. We can specify how much erosion we want and what type of erosion we want. So for example, we can specify what extremeness the erosion should be at. So if you want the erosion to drastically drag contents from the top of a hill down to the bottom of a valley, you can bump that up a lot. Or if you wanted to, barely smooth anything out and just like look like some slight rainfall touched it, you can also do that. And this is all done in Lua, which is a scripting language if you guys aren't familiar. Meaning that it's all done in real time, and it's really nice because you can change very drastic things. These are the actual functions that are being called from the engine when the train is being generated. So you can change these to be very, very different. Like you can actually have your entire logic for your train management code here. In the end, it's actually reconverted and parsed back to C, so you don't have the performance overhead of a scripting language, but you do have the nice ease of access of the scripting language. Now, continue on. This is just a basic config file. It allows you to specify things like the amount of pages in each direction you want to be loaded. So if we bump this up to like, or it would be easier to see if we bump it down to like 2. So then we'll go ahead and regenerate. So as you can see, now it's only generating 2 in each direction. This had no effect on the actual terrain generation, as in the values. It changed because we changed the script file to be different values, but that actually had no effect. And as we can see, if we bump this up to like 10 right now, it's going to take a second to load. Oops. Because this is more radius than we were using before. And the thing is that right now we're generating new train, as in this isn't saved, so it's going to take longer because as a rule it's always longer to generate new train using the noise functions than it is to read it from disk, which is kind of weird to think about because like in this day of age, one of our biggest overheads on computers is actually the bus and transferring data in memory, but in this case it's actually much faster to get it from memory because the overhead of generating noise is so much higher, on top of the fact that usually when you save these things to file, you can do so in such a way that data is very local and contiguous. So polling things is more of like pulling a huge group of things, as in you pull the entire page as opposed to an individual block or element. Alright, so we have our train back. As you can see, it's a much larger radius now. Things load relatively quickly, even at large radiuses. Like this is a huge amount of data, and to compare it to something like Minecraft, which you might be familiar with, Minecraft loads in a 9x9 radius, or 9 radius, with 16 by 16 by 16 chunks or pages of data. We're loading in a 10 by 10 by 10 radius, but we're loading 32 by 32 by 32 chunks of data. So not only is our radius higher right now with very little lag and very little overhead, but it's also much, much, much bigger pages than Minecraft Double. So this is actually about triple in cubic volume the size of Minecraft render distance by default, which is just a good metric to use because, Minecraft is kind of the yardstick or the point you want to reach now. So outperforming them is always kind of nice. Continuing on, basically, the train generation is not something that I'm explicitly creating. Like I'm creating the tools that you can use to create terrain. I'm not actually creating the finalized terrain because I'm not really interested in that part of it. Like I like doing the math and the actual structural and back end, but actually creating the game part of it isn't all that interesting to me. So the train is probably going to stay in a form like this for the foreseeable future. Anyway, so that's about it. The last thing I'm going to show is I actually have another project I was working on for the voxel thing, but it's only semi-related. So this is something that I built to test my UI, because I built all the graphical user library by myself. This is all from scratch. It's using raw OpenGL and C. So to test it out, I decided I was going to build a mock-up or representation of the Conway's Game of Life, which is a famous game in cellular automata, which I was really interested in for a while. I'm going to use it to use water physics in the physics engine to represent realistic water in a voxel environment. Alright, so you can just go ahead and start drawing or whatever, it doesn't matter. And then we start playing it out, and it goes through the generation sequence that Conway's Game of Life does, for those of you who are familiar. It's basically just evaluating every single update with a very distinct set of rules, and these rules are very famous. You can look them up on the wiki. And I've added features so you can like change the speed, the generations. Surprisingly, after a while, if you up the speed enough, you actually start lagging, because Conway's Game of Life is quite resource intensive if you're updating things quick enough. You can also pause it. You can restart it. And that's basically it. So thanks for watching. If you have any questions, just let me know.